Well, we're back, CNBT 1311 for chapter 11. We've got one more chapter to go. This has been an unusual ride. It does seem that we have been able to cram this into 8 weeks online at the last minute. So what's it like flying in an airplane while we're building it at the same time? I think we've done all right. So far, y'all done good. Just keep it up. We're almost done. Mechanical and electrical systems. Oh my God. If this was a 16-week face-to-face course, actually this whole chapter could be a whole semester. In fact, it was when I was in college. But like I said, I'm a former engineer. I've done a lot of HVAC calculations, heat gain, heat loss, MRT, you name it, blah, 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 blah. But this is really, truly outside the normal scope of an architectural designer or a construction manager. You need to understand the vocabulary, and the best thing to do is understand the basic vocabulary so you know if you're getting BS'd by your subcontractor or your mechanical engineer. The mechanical engineer that did the Cypress Center, in my opinion, was a moron, with all due respect to him. Later on, there was a female engineer that worked for him, and she actually had some smarts. I enjoyed fixing some problems they should have fixed up front after we opened the center in 2013. But the head guy was off the rails. He and I had a lot of arguments. And in fact, I just flat told him, I said, you are not going to do this. But anyway, that's a whole nother story. Let's get on with this. I will try to make this as painless as possible and give you some vocabulary and some understanding. Again, if this was a 16-week face-to-face, I'd actually have you do some basic HVAC calculations, just so you could experience the joy and pleasure of what we go through, but I will save you that. All right. Hot water heating. This is a pet peeve of mine. If the water's already hot, why are we going to spend the money to heat it? I know I'm being snarky. Anyhow, let's move on. In here's electrical wiring. I mean, this is electrical engineering stuff. We will talk all about that, but don't worry, okay? Here's a good ISO of a mechanical, of a air handling system, HVAC system, whatever you want. This looks like a stacked unit, and there are some benefits of having a stacked unit, where your air handler is inside the structure, and this is a representation of hard, excuse me, hard ducting, metal ducting, which is a high-end commercial HVAC, not the crap they put in our houses with that flex duct. I hate that flex duct. Vermin like it because they can bury into it and run up and down your ductwork. And don't buy into the fact they come in and steam clean your ducts, because if you've got that flex duct, that steam cleaning is going to tear it all to hell. Excuse me, it'll tear it all up. I guess I need to go to HR jail now. All right. So like I said, this chapter discusses the mechanical and electrical systems, which includes lighting, ventilating, heating, plumbing, sewage, blah, 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 blah. All right. Ching has this explained later on in the chapter, but since it's in the first page, I'm going to go ahead and do a spoiler alert. This is a top-mounted sink We talked about top-mounted sinks and underhung sinks in a previous video. You have to have potable water coming in. That means the stuff you can drink and allegedly drink. And then you got to have wastewater out. And wastewater is either black water or gray water. Coming out of a sink like this, it would be gray water. Black water's coming out of the toilet. None of it's potable. It all goes in the same sewage treatment system, and it's all treated. It's all treated the same. This riser here is a water hammer riser. It's what I call a water hammer riser. It helps abate the water hammer. There's a little air column in here, and air is compressible. Liquid is not. This is a P-trap system. This is the J-bend of the P-trap, and this is the tailpiece that's coming out of the drain on the sink, and this is the wall tube. We call it the wall tube because it goes through the wall. Yeah, see how smart we are when we name this stuff? And you thought us Ingham and Meneers were really intelligent people. Anyhow, the weir. What is a weir? A weir is a plate that we use in water and wastewater treatment. The water level comes up. It's just a plate. The water level comes up, and then all of a sudden, it just gently flows over into a catch channel going for the previous treatment. In a clarifier, all the sludge is down here in the bottom, and we'll draw the sludge off to the sludge digesters, and then this is the clarified water that's picked up and then taken for other treatment. All right, let me erase that. Okay, now, so what a P-trap, what does it do? It traps water in here, and it gives you a gas seal so that the sewer gases, which is H2S, hydrogen sulfide, and that's the rotten egg smell. So if you're in a building at the Cypress Center, the classroom CY129, there's a storage room right behind the concrete masonry unit wall, and in that storage room is a floor drain. And about once a year, depending on the relative humidity and how hot it is and how much air is being sucked as the makeup air out of that storage room, the P-trap will evaporate, the floor drain, and then you'll start getting sewer gases into the classroom. So I have the facilities people take a 5-gallon bucket of water and go recharge the P-trap. Again, that's the benefit of having a not forward-thinking mechanical engineer when they lay that stuff out, because he's pulling his makeup air out of that storage room for that section of the building. But I digress. Let's move on. This is a power panel or a breaker panel, whatever you want to call it. That's the main breaker, and here are the branch breakers. This is for a residence. This is all going to be single phase. Power is either 3-phase or single phase. There's high voltage 3-phase, which is 480, and then low voltage 3-phase we consider 240 volt. And there's benefits to having 3-phase as opposed to single phase. Most of your residential stuff, well, all your residential stuff is single phase, which means it pulls more wattage. If you had 3-phase power coming to your house, for a given horsepower, a given wattage drain, you'll be pulling less energy. I think 3-phase power is more efficient, but it's also more expensive to pull it in. I've got 3-phase power running along the road bordering my property, but I can't get 3-phase power into my house without paying large sums of money to the light company. All my equipment, my shop is single phase. And you can get phase converters. So you can convert a 3-phase piece of equipment to single phase with a static phase converter or a rotary phase converter. But anyway, I digress. This is a switch. That's a symbol for a switch. And if it was up to me, there'd be a course in your drafting program on electrical circuit design. Instead of some of the wasted classes the curriculum team has in there, like statics and strength of materials and that kind of stuff. But nonetheless, let's move on. This is the water heater. You'll notice I said water heater, not hot water heater. I don't want to be a Forrest Gump. And this is a stacked air handler. I had a stacked air handler when I had a ranch house, 300 acres, years ago. These are convenient because you can service them with inside the structure. You don't have to crawl up in an attic space. But they do take up more floor space. All right, thermal comfort. These are some terms you need to understand. What is conduction? What is convection? What is radiation? He explains it very good here. What evaporation? You know, any of y'all been out jogging or playing soccer? I'm 69 years old and I grew up playing soccer here in Houston, believe it or not. My father called it communist football. But I enjoyed it. Made a lot more sense than putting on pads and a helmet and having the way beat out of you by some guy that was like 400 pounds and had no fat on him. But anyway, I enjoyed soccer. Played it up until I was 40 in senior men's league till my knees gave out. But nonetheless, again, I guess this is what happens when you get old, right? You just start rambling on about nebulous stuff. Well, anyway, so conduction, convection, radiation, and evaporation. And you've been out jogging, playing soccer, and you come in an air-conditioned house and you start getting the chills, right? It's because the sweat's evaporating off. Problem down here on the Gulf Coast is the reason evaporative coolers don't work like they do out in the Nuevo Mexico or Arizona is because the humidity's so bloody high down here. The evaporation process is really, really slowed down to almost nothing. Okay. So let's move on to comfort zone. What's this up here? Thermal comfort. And then we have a comfort zone. Now remember in chapter 9, we talked about ventilation of a bathroom and the ventilation of a kitchen. Ching used a baseline of 5 air changes per hour, and the kitchen was 2. This is really low, and I told y'all that in that video, and I'm going to tell you again. Shame on me for not doing this calculation back over there. For a kitchen, 2 is extremely low. For commercial kitchens, we're looking at 15 air changes per hour, and an ACPH is air changes per hour in cubic feet per hour. All right. Fans are generally rated in cubic feet per minute, CFM. And just go out to Home Depot or Lowe's and look at their exhaust fans for bathrooms and kitchens and stuff like that. And you'll see that, you know, they're sized. So you take cubic feet per hour and you divide that by 60 because it's 60 minutes in an hour, right? And you get cubic feet per minute. So here's a calculation up here I did before. So let's just assume we have a 10 by 10 by 10 foot space. So that's 1,000 cubic feet. And we want, let's just say we want 10 air changes per hour. Well, that's 10,000 cubic feet per hour. So you divide 10,000 cubic feet per hour divided by 60, and you get 166.666, what my ex-wife thinks I had tattooed on the back of my head. And it just goes on, way heck out here. 6666666, and then 7. Well, I just did it to 4 decimal places. All right, so we need 166.6667 cubic feet per minute. So you'd go pick a minimum fan, an exhaust fan, that would do 167 CFM, cubic feet per minute. It's just that simple. So Factors affecting human comfort include your air temperature, your relative humidity, your mean radiant temperature, air motion, air purity, um, sound, vibration, and light. Um, we're talking about the environmental design of a space. Okay. Um, and speaking of environmental design, a lot of architecture programs have a 4-year environmental design degree. None of them are accredited by the National Architectural Accreditation Board. Those programs are 5 years. I'll give you an example. A&M sold that environmental design degree, and their idea was to force you into staying 2 more years for your master's in architecture, which is accredited, which will allow you to take the state exam for being a professional architect. Now, this associate degree for architectural design is an AAS. It's not accredited, but we've had some students that wanted to go on and become real architects. My advice to them was to pick a 5-year, whether it's Texas Tech or University of Houston main campus. They've got a good architecture program. Prairie View A&M's got one, and do the 5-year program. And U of H downtown has a 4-year short track. They call it environmental design, just like A&M does. But nonetheless, I digress. Again, that's that old man coming out in me, I guess. Air temperature and mean radiant temperature. Mean radiant temperature is MRT. This is important to thermal comfort. All right, we'll have a diagram about that in a minute. The higher the MRT of the surrounding surfaces, the cooler the air temperature needs to be or should be. Okay, and there's a picture of this or a diagram of this. Okay, MRT has about 40% more effect on comfort than air temperature. All right. You can read all of this, and you're responsible for it. Air temperature and relative humidity. Relative humidity is RH. Here's the definition for that, and it's the ratio of the amount of water vapor actually present in the air to the maximum amount that the air could hold at the same temperature, expressed as a percentage. You got a high humidity, cold day, you're going to have dew on your car windshield. Okay. The higher the relative humidity of the space, the lower the air temperature should be. During the summer, we got high humidity. You go out and you watch the drain line coming out of your DX unit, your direct exchange unit in your house, and you'll see the water pouring out. I've got an exterior drain on mine. I do not like interior drains. They plug up with slime and crap, and you've got to periodically go up there and put pellets in it. And there should also be an overflow switch to shut the whole unit off if the drain pan's clogged up. So when I redid mine, I just ran it outside to a French drain. Some people collect that water. It's considered non-potable water, and you can use it to water your plants and that sort of thing. Plants don't mind. The relative humidity is more critical at higher temperatures than within the normal temperature range. And then low humidity, less than 20% is undesirable effect in buildup such as its static electricity and the drying out of wood. High humidity can cause condensation problems. So you've got to balance your relative humidity. We call that in the HVAC world air balancing, where you're balancing the volume of air going into a space, the volume of air coming out, the relative humidity of the air. And y'all are probably beating your heads on the desk right now, asking me to please just stop. Again, I'm not going to beat you up over this. These are definitions. Air motion. Okay. Air motion, which is the velocity of the air. It increases the heat loss by convection and evaporation. And you go back up to these definitions of convection and evaporation and get an idea of what that is. I'm going to have to be really, really careful because the last 2 weeks of this course, which this video covers, well, the one before this one in chapter 12, you don't have 14 days. You've only got 10. So we're going to water this down as best we can, make it as painless as possible. All right, air temperature and air motion. Okay, I just said that the air motion is the velocity of the air. Velocity is a vector quantity as opposed to speed, which is a scalar. And that means absolutely nothing to y'all, and I don't even know why I said that. Maybe I'm just being a geek this morning. All right, the cooler the moving air stream is relative to the room air temperature, the less velocity it should have. Well, that just makes sense, right? Air velocity should range between 10 and 50 feet per minute. Okay, FPM, 50 feet per minute. All right, if you're a metric head, this is in meters per minute. All right, higher velocities can cause drafty conditions. So what does this mean? 10 to 50 feet per minute. That just means the 10 is 0.113636 miles per hour, and the 50 feet per minute is 0.568182 miles per hour, and I am sure y'all are just really impressed over that. Air motion is especially helpful for cooling evaporation in hot, humid weather. Yeah, because if it's hot and humid and you're sitting on the back porch drinking your bourbon in the afternoon and smoking a fine Nicaraguan Maduro Churchill cigar, you're going to want a fan on. So the higher that fan velocity, the cooler you'll be because it's wicking away the sweat off of you and making the air cooler. It helps with the evaporation. Okay. Feet per minute divided by 88 equals miles per hour. Feet per second divided by 1.467 equals miles per hour. And I'm sure y'all are just excited to be given that. Because when you're reconstructing a motor vehicle collision, you convert miles per hour to feet per second, so you can work your rotational momentum and physics out when you're calculating all the nuances. Psychometric charts. Oh my God, this is thermodynamics in engineering. Oh geez. Okay. Wow. Okay, buckle up, buttercups. All right. A psychometer is an instrument for measuring the atmospheric humidity consisting of two thermometers, the bulb of one being dry and the bulb of the other being kept moist and ventilated. And guess what? In today's digital world, we have digital psychometers. And this is not psychometers, it's psychrometric. Okay. Although, getting into reading this, you would think it's a psychometric chart for some psycho person. Enthalpy is a thermodynamic term. If you take engineering, you will have to do enthalpy and entropy. It's the measure of the total heat contained in a substance. It's equal to the internal energy of the substance plus the product of its volume and pressure. The enthalpy of air is equal to the sensible heat of air and the water vapor present in the air plus the latent heat of water. And oh my God, y'all are probably ready to jump out of a building right now. All right. The dew point, you probably have heard dew point before, is the temperature at which air becomes saturated with water vapor. Okay. Then you have wet bulb temperature, and your comfort zone lies somewhere in the happy space in here. Okay. Y'all chill out. I'm not going to beat y'all up over this. Okay. Here's another term that sounds really cool. You can do this at a party or something, and people will move away from you. Well, you know, the adiabatic heating is a rise in temperature occurring without the addition or removal of heat. And your friends are going to look at you like, yeah, okay. That's the adiabatic heating. as when excess water vapor in the air condenses and the latent heat of vaporization of the water vapor is converted to sensible heat in the air. And you're just screaming right now, I know, stop it, stop it, stop it. All right. These are all things that us HVAC engineers have to take into account, and when we're trying to come up with a somewhat livable space. All right, mean radiant temperature. Mean radiant temperature. You'll be asked about this. If you don't get anything out of here, just remember MRT. Mean radiant temperature is the sum of the temperatures of the surrounding walls, the floor, and ceiling of a room. It's weighted according to the solid angle subtended by each at the point of measurement. Oh my God. Okay, well, what the hell does all that mean? All right, you got wall temperatures, you got wall temperature over here, you got wall temperature over here, you got floor temperature, ceiling temperature, and they're all going to converge at some point in the room. You've probably all been in a room where you're maybe you're sitting, your computer's in the corner, and the air is just dead because you're not getting enough airflow. So you bring a fan in to stir some air around, and what you're doing is you're trying to balance out all the MRTs in here. Okay, so here's a fancy formula. That's the mathematical symbol for sum of all the temperatures divided by 360 around the humanoid. Okay, so you're not overloading your antiperspirant or your deodorant. Okay, that's about as simple as I can make it. All right, and what that means is you've got to calculate all the heat generating thing, or the negative heat generating. In other words, it's sucking the heat out, and includes the floor and the ceiling, and all the heat load in a room, lights, equipment, people. Um, Humans generate, I think, if memory serves me correctly, somewhere around 700 BTUs per hour. We'll get to that later. Okay. Um, we'll get later. We haven't said that yet. I mentioned, I think, in a previous video something like 1500, but that's if you're doing hot yoga or aerobics or something like that. Just sitting on your duffs, I think it's around 700. All right. All right, but don't quote me on that. We'll find out in a little bit. All right. Heating and cooling systems. Man, they're all cons. If you've got a basement, you can put the furnace down here. Okay. Theoretically, you put your air conditioner down here if it's a stacked unit. Most of the DX units will be on the outside or up on the roof as RTUs. And this is talking about the balancing of the relative humidity, the mean radiant temperature, the MRT. Air motion is important. We've talked about that. Air motion inside, and we need some kind of air exchange, right? If not, this is going to get stale in here and people will start getting sick. Um, that was a big deal during COVID. All those morons talking about COVID, they didn't understand about air moving and exchanging fresh air with stale air in a building. And over in China, when they locked all them people in their apartments and they wondered why they got sicker and sicker and sicker. Well, guess what? You got them in a freaking igloo cooler. Go figure that. Um, um, the traditional fossil fuels, gas, oil, and coal, um, are an extremely efficient um, way of producing heat and energy. Electricity is, he calls it a clean source. All the greeny weenies still say it's um, 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 clean. It's only clean at the site because you're bringing in power lines, okay? But what generates electricity? It's either gas, oil, or coal, or nuclear. And why we haven't pushed not fission reactors but fusion reactors. Fusion reactors produce a lot less radioactive waste, and they're a lot more efficient. But everybody's afraid of them. Oh my goodness. Well, the reason most of the plants don't work is because the federal government's got it so highly overregulated that, and a lot of those people with the Nuclear Regulatory Commission, they don't know their rear end from a hole in the ground, some of them. But nuclear is extremely efficient if it's done and managed right. Okay, and he talks about fission. Fusion, in my opinion, is a much more efficient form. Got to have fission to have fusion, but it's much more. Fusion is much more efficient. Now, if at some point in time we can get the Mr. Fusion, like in Back to the Future, where you can drop a banana peel in what's left of a beer can in your Mr. Fusion to separate the molecules and power your DeLorean time machine. Maybe someday we'll get there. That would be cool. Hydrogen is a very efficient form. H2, hydrogen. Hydrogen's around everywhere. The sun burns hydrogen, creates helium, which means the sun's expanding because it needs a greater volume to burn off helium at the same rate as it does hydrogen. So yes, the sun is expanding. And in a couple of gazillion billion years, it will get so expanded that it'll swallow the first 3 planets, supposedly. Oh my goodness. Oh, run for your lives. NEM, NEM. All right, hydrogen is Toyota's working on hydrogen cars. So is Honda and General Motors. They've got a consortium together. The Viking cruise line, I talked to their engineers on the Viking Explorer, science explorer ship that I spent 2 weeks on in the Great Lakes doing biological research with people that are a lot smarter than I am. I was their flunky. They had 2 submarines on that one. That's pretty cool. Go down into the depths of the Great Lakes. But their 2 new explorer ships will be hydrogen electric. They're burning nav gas now to power the generators, but their 2 new ships will be hydrogen and to generate the electric power for the electric motors that drives the ship. What happens when you burn hydrogen? You end up with water vapor, H2O. Dihydrogen oxide. So, anyway, now the problem with hydrogen cars, just like electric vehicles, is how do you fuel them? I mean, I don't know too many Valeros or Shell stations that have a hydrogen pump yet. So we've got to get the infrastructure done. Okay. Let's see, more than 40% of all the energy and more than 65% of all the electricity in the United States are consumed in our buildings. Everything that drives. So, yes, electrical is efficient. You can transmit large amounts of power over cables in the air, but it still takes fossil fuels to create the electricity. All right, we have solar energy. We have wind power. That's a boondoggle. It takes thousands of gallons of lubricant that has to be replaced every year for wind turbines. When the wind's blowing, yeah, they work great. When the wind's not blowing, they don't work worth it all. They're no good. It's just like solar panels. When the sun's out, great. Okay. And when it's not, you don't get any power. When the wind's blowing, you get some power. Now, you go out to Sweetwater, Texas, the wind energy capital of the world, and um, um, you'll see these. These blades are extremely long. They're made out of fiberglass, which fiberglass comes from the petrochemical industry. It takes oil and chemicals, and the majority of the refineries, um, gasoline and diesel and lubricating oils are a byproduct. Most of their money is made off of chemicals, petrochemicals. Um, these things have a life cycle, the blades, of about 10 years, and then you cannot recycle fiberglass because it's a thermoset resin, and so they cut them up and then they bury them in the ground, and they will be there for hundreds of thousands of years. Um, so, is it clean energy? No, it's really not. But if you can balance your solar and your wind and your conventional power generation methods, it helps. But solar energy is not your savior. Wind energy is not your savior, um, despite what the greenie weenies want to tell you. I did solar and wind research back in the 70s when I was at A&M as an engineering student. Um, the carbon footprint to make solar cells and um, wind turbines is much higher than a conventional power plant. In fact, it takes, if you combine all the commercial airlines, and we're talking about FedEx, everything, all the commercial airline, the amount of fuel that they use in 1 year to deliver packages or people or anything else, that amount of energy only equates to 250,000 car batteries for electric vehicles. 250,000 is all. So, is EV green? No, it's really not. All right, biomass. This is where you'll have it's organic matter makes up plants to produce electricity and transportation fuels, chemicals that would otherwise be made from fossil fuels. All right, well, okay, fine, whatever. All right. Um, um, yeah, wood burning stoves. We talked about that. My Traeger grill uses wood pellets. Um, Corn for ethanol. That was a boondoggle. Mexico got super pissed off about that because you can't pipeline. You can't run ethanol through a pipeline. It has to be trucked in tanker trucks. And the price of corn went way up, and because they were turning a lot of the corn into ethanol, um, and so the price of corn for food went up. The supply of corn went down. So the agave farmers in Mexico got this bright idea: if it takes 10 years for an agave plant to mature, so we can make tequila, well, we're going to plow up all our agave fields and start planting corn. And the Mexican government went in and said, "No, you're not. Tequila is the national byproduct. I mean, the national product of Mexico. You're not doing that." Um, um, when I was, I had for about 5 years, we did a lot of landfills, and some of the landfills, if you could separate the wet garbage from the non-decaying garbage, um, you could generate methane gas from the landfills, and that's biomass. And then take the methane and run it through a engine to generate electricity. Um, some consider biomass to be carbon neutral fuel because its burning does not release more carbon dioxide than that's captured in its own growth. I disagree with this statement. I would beg to differ. It helps, but it's not carbon neutral. In order for this stuff to produce any kind of burnable fuel, it's carbon. Period. It's just the physics of the universe. Um, um, Now, he does make a statement here: the conversion process of biomass into fuel can be energy negative if more energy is required for the conversion process than is obtained from the product. I just said that about car batteries, total EV batteries. Just to produce 250,000 batteries for Tesla's cars, you're consuming all the fuel it takes to fly every commercial airline in 1 year around the world. That's everybody's commercial airline. So, to me, that's energy negative. Hydrogen, we just talked about hydrogen. Hydrogen is the most abundant element in the universe and on Earth, and it can be found in anything. Okay, so if you could actually come up with a gizmo to split the hydrogen off of water without spending tons and tons of energy to do it. Now, we can do it, but you're putting in more energy than you're getting out. So it's energy negative. All right. But when you burn hydrogen, you get water vapor, and we've already talked about that. Where are we at on time? We're at 41 minutes. More alternative energy. Hydropower. This has been around since the dawn of time. Whether it's an old grist mill that's got a water wheel or hydroelectric dams. We've got hydroelectric dams in Texas, believe it or not. Got hydroelectric dams everywhere. Dam up a river, like Hoover Dam, and I went through and toured a huge hydroelectric dam that was made during the WPA project during the Depression that's generating electric power still up in Branson, Missouri. You got your turbine house down here in the bottom. Water flows down here, spins the turbine, generates electricity, and out you go. As long as you got rain and water and you're not in a drought, then this works great. You can use submersible electric pumps and spin them backwards, and they'll generate electricity. The Fleet Pump Company in Sweden. I spent 2 weeks inspecting pumps that we had on a big project in Sweden, and in Sweden they got a lot of what they call low water dams. They're not real deep, but they have cascades of low water dams, and they use those submersible pumps to polish the electric grid. In other words, they'll generate small amounts of electricity for a small village community, and they tie it into the electric grid, and it works very well for them. That's hydropower, hydroelectric power. And there's a lot of benefits that can come from hydroelectric power. Flood control, you name it. Ocean energy. Now this is kind of neat. In certain parts of the world, not only do you have waves coming in, but you have high tidal ranges. Over there in England and some places on the English Isles, when the tide changes, the tide can change upwards to 12 to 15 feet from low tide to high tide. So the surge, whether it's a wave or the tide coming in, when it's surging in, it can drive the turbine. And they use a lot of the Fleet's submersible pumps. They reverse the poles on them, and when they're spinning, they're generating electricity. And then when the tide or the waves receding, the turbine spins backwards, and then there's a pole switch box up here that reverses it back, and it generates electricity coming back on the retreating wave. That's ocean energy. And there are other people that had invented movable panels and stuff that would move back and forth. All right. Let's see. Ocean thermal energy conversion is what is the acronym. OTEC. Okay. Convection. I've got a 12-foot diameter pipe that's made out of high-density polyethylene spiralite that goes miles and miles and miles down into a Pacific trench over off of a small island in the Philippines that we use to convect cold water from deep down in the Pacific Ocean for a cogen plant for a village that didn't have any electricity or any potable water at all. So we drilled a deep well and made it available to convinced the company to make it available to the villagers and the people that live there. And not only did they get electricity from the cogen plant, but they got potable water. Here's a neat thing. And down around the Pacific Rim, the Ring of Fire, Yellowstone Park sits over the world's largest caldera. That's a dormant volcano cap. That's what makes all that steamy, hot water for the geysers. And some of the lakes up in Yellowstone are so hot that it'll boil you. You're like a lobster. You're not supposed to swim in it. In fact, there was a young man that took a swim in one of them. He was probably intoxicated and ended up getting cooked like a lobster. But why they don't have geothermal energy systems up in Yellowstone is beyond me. It's clean. It's not hurting the environment at all. And you're using the geothermal reservoir, or the heat from deep down in the earth, to generate hot water and steam that comes up to a turbine, and that turbine then goes through a reduction gear to a generator, and it generates electricity. Now the metallurgy that it takes for this is, you've got to be careful, because this hot water, we pump saline down in here in one of these projects to a coil, and you got to be careful with the metallurgy, or your drill casings would get eaten up. And but this is a very efficient way of, if I drew it right, well, that's a short circuit, of generating heat. But like anything else, the greeny weenies, they want their electricity, but they don't want it in their backyard. But you can put one of these stations in and hide it; nobody'd even know it's there. But that's geothermal energy. Where are we at? Yeah, we're on page 9. God. All right, let's break this here, and this will be 11:2 video, and we'll see you on the next video.